Okay, welcome everyone to the last lecture of my little course. So today we are going to see something that we haven't discussed yet, which implies evolution equations. Evolution equation is another way of saying how do you separate out the perturbative from the non-perturbative part, and how do they depend, how do you compute the scale dependence, okay? So Stefano told you that the PDFs and the fragmentation function depend on the momentum fraction x, and then they depend on the renormalization scales, which are mu for the PDFs, mu n psi, the rapidity for the TMDs, but indeed they also depend on the scale q, okay? And so you have evolution equation which tell you how they depend on the scale, and these are called the evolution equation. And then once we understand how to separate the perturbative from the non-perturbative contributions, we will also try to understand how you match the two computations, and the matching is also what you will put your hands on during the exercise classes by Andrea Signori. Okay, so now let's try to understand what we're talking about from a sort of historical perspective. So we consider a Drellian process just for historical reasons, because it was the first one to be studied at this level. And you can use perturbative QCD, and you can make a fixed order calculation. So you take your perturbative QCD, you decide at what order you want to truncate your perturbative expansion, and you do your computation. And then you compare your computation with the experimental data, and you see that your computation doesn't do too bad when PT, this is the momentum, is what we usually nowadays call QT, is the transverse momentum of the photon in a Drellian process. So if QT is large, you do pretty well. But you have a problem when QT becomes small, because your perturbative computation goes to infinity, diverges, right? Whereas you see that the experimental data hint to a completely different behavior, certainly not divergent, okay? So you do have a problem with perturbation theory, and what you can say is, I use a completely phenomenological approach. And I say, I correct for a PT or QT dependence, which looks like this one that I see from the data, okay? And you see the data do go to smoothly to some finite value. So you can guess that this dependence could be represented by a Gaussian, basically, right? So you correct the cross-section which shoots up at very small QT with the Gaussian behavior, right? And you also, so this is the Gaussian, and you normalize the Gaussian in such a way that when you integrate it, it goes to 1, and so it doesn't give you any problem with the integrated cross-section. And then you go and take, so you're exploring small PT, so data which are sensitive to the small PT behavior of the cross-section are data which occur at smaller energies. So you select out a set of data which correspond to smaller energies. These are data from Fermilab, and you make a fit. And you see that actually at low QT, the data do follow a Gaussian distribution. And you can make a pretty good job of this. And the only thing that you see is that the width of the Gaussian that you need is different according to the central mass energy that you're considering. But your Gaussian hypothesis works quite well. So you say, okay, solve the problem. And you haven't solved anything, because if you take another set of data, these are CDF data from Tevatron, and the center of mass here is around 1 TeV. Then you see that your Gaussian computation works well at small qt, but it fails really badly at larger qt, where your perturbative computation could do much better. So the situation you are left is this one. You can do pretty well at large qt with your perturbative expansion, but you fail badly at small qt. Instead, if you put in a Gaussian, you do well at small qt, but you fail badly at large qt. So what are you missing here? Do you know what do you have a guess? What am I missing here? You know now, okay? What am I missing? I am not taking into account the fact that when the quark moves, okay, within the perturbative region and out, when scale separations become larger and quarks and gluons start to hadronize, the quarks can radiate gluons. And if you don't take them into account, this radiation into account, your computation fails badly. So what you have to do is to study the effect of the radiation of gluon, and in particular of the radiation of soft gluons. And here I hope you remember what we were discussing yesterday. And you have to correct for the effect of this radiation. In the past and in the collinear community, these taking into account the radiation of soft gluons is called resummation, okay? Whereas in the TMD community, this is often referred to as TMD evolution or TMD factorization. John Collins is very happy with TMD evolution and very unhappy with resummation. He says resummation is a word which doesn't mean anything. So you can make your choice. If you conveniently take into account, sorry, if you appropriately take into account this radiation, you can write your cross-section, and I stress that this cross-section is differential in QT, so it picks up the detail of the QT dependence that you are interested in a nice and separated way, in which there is a term which is a term which is called the W term, okay, which is initially divergent, but you resum it and you make it convergent. And another term which is finite since from the very beginning, which is called the Y term. And the Y term is important for the matching. So for matching the small QT region with the large QT region, which means matching non-perturbative to perturbative regimes of QCD. Now, how do you get to this form here? The first thing you have to do is to Fourier transform into the QT conjugate space. And I've already told you yesterday, why do you do that? Why do you make your life so complicated? You have to do Fourier transforms all the time. Well, you do that because when you take into account your radiation, the radiation of subsequent gluons, you have to conserve momentum in each and every vertex, for each and every radiation. So you have a complicated delta function in the Feynman diagram, which has to ensure momentum conservation. And these momentum conservation laws are much more conveniently taken into account in the BT space, okay? So you Fourier transform to the conjugate space, and you write your cross-section. And remember, this is crucial. I'm not talking about TMD yet here. I'm talking about cross-section. So this is sometimes called the CSS1, the Collins-Soper kernel, sorry, the Collins-Soper Sturman factorization in its first version. This is a factorization and a TMD evolution which is worked out for the cross-section. We're not separating TMD's hard part. There's no hard part here, okay? So you can do it for the TMDs and we'll see it in a minute. But for now, we work with the cross-section. And the reason why I go through these is that when you will do the exercise with Andrea, you will need to know what is the W and the Y term. And the W and the Y term are pieces of the cross-section, of the full cross-section, where you don't yet separate out the distribution and the fragmentation function. Okay, so you go into the Fourier conjugate space, and you write down your cross-section. And you end up with a finite term, which is what you call Y. This is regular, okay? And you find yourself with another piece, which is divergent. And you have to do a little bit of acrobatics to make it converging. And the way you do it is you parameterize it with a Sudakov factor. Okay, I think Stefano told you about something about Sudakov yesterday. We are not going to dwell into this because we have to do many more things. But you do a little bit of acrobatics, as I said, and you come out with an expression which is like this. It looks like this, where you have written your cross-section as the W plus Y, okay? So W is the resum part, which is devised, the W term is devised to work well when Qt is very small. So in the region where Qt is much smaller than the hard scale Q, okay? In fact, John Collis would tell you that the way W is devised is to work down to Qt equal to 0, okay? But if you want to have a unified description of the cross-section over all the possible values of Qt from the non-perturbative small Qt regime up to the large Qt regime where you are fully perturbative, then you want to have a scheme which works all the way through. And collinear factorization, which works when Qt is large, doesn't work at Qt equal to 0. So you have to give up on that, okay? So the W term works down to Qt equal to 0. But if you want to use TMD and collinear factorization at the same time, simultaneously, you have to give up on Qt equal to 0. But you can go down to Qt smaller than M, and M is a small scale mass, okay? Now, what is the problem of this scheme here? Well, the problem is that your W term, which is devised to work really well when Qt is small, fails badly when Qt gets large. And you don't have to go to very, very, very large Qt. The W term becomes unphysical pretty soon, okay, when you move to larger Qt. And it becomes badly, nastily unphysical because it goes to 0 and then it becomes negative. It drops down really quickly. And this is something that Andrea will actually allow you with this little code that he will share with you to experiment with, okay? So you will be able to move the value of Qt and see where W goes to 0 and becomes negative, okay? For which Y, and of course, everything depends on the value of Q. If Q is very large, you have a large lever arm where you can work. But when Q is small, so when you go to lower energy processes, then you have very little space to move on, and then you will see that your W becomes negative very, very quickly. Instead, the Y term is finite, so it doesn't give you any problem, but it plays a crucial role because it corrects for the antiphysical behavior of W when Qt becomes small, and it gives you, by summing, by sum, a physical cross section. Okay, so basically your cross section is W plus Y. Okay, and W works when Qt is devised to work when Qt is very small, but it fails when Qt becomes large. So it does these, right? This is Qt. So this is W, okay? When this happens, Y comes in and helps you. And what does is it provides you with the contribution that you need to make your cross-section nice and smooth, and possibly match it to the large Qt tail, which you can compute. So Y, the definition of the Y term is given here. So you can compute the Y term by taking the fixed order cross-section and the asymptotic limit of the cross-section when Qt is small. You take the difference between these two. So these two diverge at small Qt, and if you take the difference between them, you get something which is finite, okay? And it helps you in the central region, in the matching region here, right? Did I tell you everything I wanted to tell you? Okay. So this is what I told you. The W term becomes unphysical at larger Qt when Qt is equal or larger than Q, but the W term should correct for the misbehavior of W. I say should because, as you will see, the matching is a very complicated procedure which most of the time doesn't work. Now, let's try to understand why it doesn't work and why it's so difficult. So from the perturbative, so from the collinear point of view, you write the W term as the exponential of the Sudakov factor times something that you will easily recognize. This is the convolution of the Wilson coefficient with the PDF that Stefano was talking to you about yesterday, right? And there are two of these convolutions because this is Drelian, so you have two hadrons, okay? And the Sudakov factor is defined in this way, and it's computable in perturbation theory. These coefficients A and B are known. You can compute them, and you compute them in perturbation theory. And here you have to integrate over the integration variables from up to Q squared from a lower scale, which is C1 divided by BT squared. Now, remember that BT is the Fourier conjugate variable with respect to KT. So BT small means large KT, and small KT means large BT, okay? Now, the issue here is that what you're doing, this kind of decomposition is purely perturbative, okay? And the problem is that when you go to large BT, which means small KT, small QT, okay, when you go down to a region of BT where, so you go up to a region of BT which corresponds to small enough KT to believe that it's non-perturbative, mu becomes too small. So basically, if this lower limit becomes too small, It means that you are pushing your perturbative description too low down in a region where you know that you're not perturbative anymore. So you want to avoid this region, okay? Because you know that your perturbative expansion breaks, right? So you reach, when this goes too small, you reach a limit where you don't trust your perturbative expansion anymore, and you have to stop. You have to stop there, because there you need to do something different. You need to put in your TMDs. You need to put in your non-perturbative models, okay? And there is a prescription to do this, which is called the B star prescription, okay? So the first step is you trade your BT variables to something that traditionally is called B star, which behaves like BT when BT is small. Small BT means perturbative region. So in the perturbative region, you work happily with your perturbation expansion, okay? As long as BT is very small. When BT grows, this B star settles to some maximum value. And this is crucial. You have, because it requires some previous knowledge, you have somehow to know or to guess what is the maximum value of BT where you have to stop, because the perturbative expansion doesn't work anymore. So let me make you another drawing. So this is BT, and this is B star of BT, okay? So when BT is small, you are fully perturbative, okay? So you're doing well with your perturbative expansion. But then when BT grows, you know that somehow, say somewhere here, your perturbative effect will become more and more important and dominant. So what you do is you take that particular expression in which BT is frozen, it's not allowed to grow anymore, to a value, this value here, which is B max. Okay? And unfortunately, B max is something that you have to guess. There's no way to compute it. Okay? So it's a little bit complicated. So you have now traded BT with B star, which guarantee that you never go into the non-perturbative region with your perturbative expansion, okay? You stop. And now look what you do. Well, this is pretty simple. You take your W term, which is devised to work well here, where you are non-perturbative. Okay, and you divide it out by the W term computed in B star. Okay, so this is the W term, which works, it's guaranteed to work in the perturbative region. Okay, you take it out, you divide it out from the full W, and what you're left is something which is purely non-perturbative. Okay, by construction. You made it this way, you devised it that way. You've taken the full W and you've taken out, subtracted out from it all the perturbative part. And this is the way we traditionally separate out the, the non-perturbative part from the perturbative part. We work at the level of the kinematic variable, BT, or in the conjugate space, BT, okay? Okay, now, as I told you, this scheme works and helps you to factorize the full cross-section. This is something that was done many, many years ago. Nowadays, we prefer to work with a factorization at the level of TMDs, okay? This allows you basically to separate, to put to separate out the hard coefficient, okay, from everything which is not hard, soft and collinear, which we define, we insert into the definition of the TMDs. But the way you do this separation, this is sometimes called CSS2, or better, TMD evolution. This is done in the same way. So you trade your BT for B star, okay? And B star is a function of BT, which is equal to BT when BT is small, smaller than a B max, and is equal to B max. It's frozen to B max when BT is larger than B max, okay? And then you take your TMD and you evaluate it at some fixed scale. This is the renormalization scale and the value of Q0. And you multiply it and divide, sorry, you take your TMD and you divide and multiply by the same TMD computed at B star, okay? And so what you are left out with is the perturbative part of the TMD multiplied by something which is the ratio between the full TMD and the TMD evaluated at B star, which is completely and fully non-perturbative, okay? It's a simple, very simple mechanism, but it's efficient, okay? It's an efficient way to separate out what is perturbative from what is non-perturbative, meaning what is reliable at small BT compared to what is reliable at large BT, okay? Now, at this stage, you have this non-perturbative part of the TMD, which you cannot compute it. So you have to, for example, model it or compute it with lattice QCD, lattice techniques, either you compute it with, you rely on lattice QCD, or you rely on some phenomenological analysis of your process by using some models, okay? One of the easiest models you can make is a Gaussian, and this is a model that Andrea will use in the code that he will show you in a minute. So you run a fit and you let the fit determine the value of the free parameters of your model, of your Gaussian, for example. Now, another way to express this is talking about TMD evolution. These considerations that we have done together lead to evolution equations. And while with Stefano yesterday for the collinear factorization, you just need to renormalize the ultraviolet divergences. So you need a hard scale, and you have equation which tell you how the function depend or not depend on the hard scale. Here, you don't just have ultraviolet divergences that you can renormalize with the renormalization group. You have to take into account rapidity. And we have talked about rapidity extensively yesterday, so I'm not going back to this. The techniques that you use are the same. This time, however, you have another scale, which is psi, and its rapidity, okay? Now, you do this exercise, you solve the evolution equation. They're not very difficult to solve. And what you learn is that the TMD, the evolution of a TMD function, contains a part which is fully perturbative, and you can compute it in perturbation theory. And there is, however, another part which is fully non-perturbative. And this is called GK. It's related to the Collins-Soper kernel, the non-perturbative part of the Collins-Soper kernel. It is this GK function. It comes straight from the evolution equation, and it only depends on BT. So it doesn't depend, for example, on flavor. It doesn't depend on the momentum fraction. It only depends on BT, and it's universal. And this is the non-perturbative part of the function which you have separate out with the B star prescription. Okay, now I have to speed up a little bit. This little scheme that I made is just for you to remember what you're going to do in a few minutes. So the exercise you will do is about matching. What are you going to match? You're going to match the W term, okay, which is devised to describe well the cross-section at very small qt. Small qt, remember, means large bt, okay? So it's in the region where your B star becomes flat. You've frozen it out. With a cross-section that you can compute at any fixed order, at any logarithmic order, which is devised and hopefully it's made out in a way that it works well when Qt is large. Okay, so you have something like this, which we have learned, which is the W term, which goes quickly to 0 and then becomes negative when Qt becomes large, to something like this, which works well in this region, but then it diverges badly when Qt goes to 0. And you have these two little things, and you want to match them in something which is continuous. Okay? So Andrea will tell you how to use the Y term, to use some specific definition of the Y term to be able to actually work out this matching in the middle. Okay? Now, these are just drawings that I made by hand. But if you want, you can actually compare with data. And a nice place to compare is using the HERA data, HERA old data, which spread out on a, they correspond to a very wide, very large Q square, and they can spread out over a rather wide range of values of PT. And this is the W factor that you can compute. And as you see, it is actually describing the data well at small qt, but then it goes to 0. And the green line here is the perturbative fixed order computation. Okay? This is an old work by... No, this is the absolute value. So this is a prediction, okay? There's no fitting. Whereas in here, there is some fitting. So you actually adjust the parameters to be able to reproduce this part. I don't think we had we didn't need to normalize this. The green line is doing very well on its own, but it was many years ago. So I would need to check to be completely sure. In semi-inclusive GIS, you usually have a problem. I have a slide about that, but I will not be able to show it now, but we can discuss it later. Okay, so this is a picture in which the matching work, and this is something that Andrea will actually help you to see explicitly. You have so you expect that your next to leading order, fixed order next to leading order computation works in the region of large Qt. You expect that the W term computed at next to leading log, for example, works well at small Qt, right? And then you use a prescription for the matching, which is devised in such a way that there is a region in which the W term computed at next to leading order is almost the same as the W term computed at fixed order. Then this and this term cancel out, and you, in this region here, you match your next to leading order cross-section smoothly here. So the green and the blue line here do coincide, their difference is 0. And as you see here, the red line, which is the next to leading order computation, is nicely matching with you can perform a match. Okay, here the black line, which is the match line, and the red line do coincide. Whereas as you move out towards smaller QT, then WNLL and W fixed order become very different. But what happens is that the W at fixed order approaches the next to leading order computation more or less in this point here, okay? And then when you take the difference between this term and that term, you are left with this term and that term in your prescription, you are left with, the cancellation is such that you are left with only WNLL, and you can match your cross-section here, right? As you may imagine, such a prescription, it relies on the fact that you have almost perfect cancellation. And ideally, this cancellation should not happen only in one point. They should actually happen over a rather wide range so that you have space enough to adjust your matching in a smooth way. If the two match only in one point with different curvature, you can do the matching in that point, but you don't get a smooth cross-section. It becomes, you get a cusp, okay, where you match, which is something nature doesn't want. Your cross-section doesn't ever have any cusp. These here, in this case, the matching work because you're a very large Q. Okay, if you go down in Q, you go down in energy, you go down in Q, okay? This is more or less the regime of the compass experiment. Then look what you have. You have lines which are all over the place. They never match in no point whatsoever in this QT range. And there's no way you can do the match. Okay, and this is something you're going to explore yourself in the next few minutes. Okay, I think I will stop here because I want Andrea to have time enough and you to have time enough to do your exercise class. So I hope this will help you through what you're going to do now, but while you do the exercises, I will make sure that the slides are shared with you. So this is my last class. But you will be able to access all my slides. And if you have any question, please do come back to me. I'm here today for a few hours, but even if you want to have some private consultation, just write me an email and we can get in touch even in the next few days. Okay? So thank you very much for following me. You've been really great, and see you next time.